Okay, so again, chapter 3 starts exponentials. We get into logs this chapter, so you can kind of like get a heads up of what's coming at you. We'll do sections 1, 2, and 3, which are exponential and the beginnings of logs, and then you'll have a quiz on this stuff next Tuesday, Wednesday, sorry. And then we'll go one more section, and you'll get a test on those first 4 sections. Part of these are going to require a calculator, part of them don't, so you can kind of keep that in mind. And there's obviously going to be graphing, so those would be on the graphing calculator part, okay? So the definition of exponential function is the exponential function f with base a is denoted as f of x equals a to the x. So it's still functions. We're still talking about functions, which means you still have that f of x involved. And then the a is called the base, and the x on this is called the exponent. A will be greater than 0. So there could be a negative on the front, but the actual base would not be negative. And a cannot be 1, because what happens if I raise 1 to any power? It always stays as 1, right? So is that exponential? Is it growing exponentially? Nope, it would be constant. That's why it can't be 1. So the first thing we're going to do is, this is our calculator part, okay? It says to evaluate the function at the indicated value of x, round your answer to 3 decimal places. So when it says rounding, that's kind of your hint that you're going to be using your your calculator. You can use synthetic or you can use graphing. It doesn't matter which one, but you want to get comfortable using one or the other. So most calculators, well, the graphing ones have a little caret that looks like this. Oops. Okay, that's what that's called, a caret. So if I wanted to find what f of x is, I would do 0.5 to the 1.2. I'm going to type in 0.5, the caret, and then 1.2. Some of the scientific calculators have a little thing that says x to the y or y to the x. Same thing. You're going to type in the 0.5 first, and then you're going to hit that button, and then hit the 1.2, and you should get 0.43527 or 3 decimal places. 0.435. So be careful with these. If I'm doing a quiz or a test on this stuff and it says 3 decimal places and you put 4, you're going to lose points for silly stuff. Don't do that. Pay attention to what the directions say. For the next one, if you've got a graphing calculator, you can type it in exactly as it says, 150, and then you can do times, and then you can do 2, and then you can do the caret, and then you can do negative 2.5. If you are using a scientific calculator there, then you'd have to, depends on the calculator, how the exponent gets put in. You might have to do the 2 to the x first and then multiply it times 150. So you just want to be comfortable with whichever calculator you're using. This is going to be 26.5165 or 17. Easy stuff, right? Okay, now we're going to talk about graphing. So when you're graphing an exponential function, which I think is interesting because there was a question on your standardized test yesterday about it, right? You had to figure out what the graph was, okay? An exponential function rises as you move from left to right if your base is a whole number, something in between 0 and not 1, obviously. It's going to something bigger than 1. It's going to increase. So if I take 2 and I raise it to a higher power, it's always increasing. If I take 3, raise it to higher power, it's always increasing, right? So that's what that graph's going to take that curve. I can never have a base be negative if that base starts out positive. Like I can't do 2 to the negative number and make it negative. That doesn't happen. It just turns into a fraction, right? So it's never going to turn negative, which means it's going to stay above the x-axis. There's actually an asymptote there. If there's a vertical shift on this graph, then it will shift it up or down, which we'll talk about and how that would look, okay? But my standard parent function of a number raised to a power is going to look like that. If the number's a fraction, think about what happens. So if I take 1/2 and I square it, what do I get? 1/4. If I take 1/2 and I cube it, what happens? 1/8. So what happens the higher I raise a fraction? It gets smaller. So that's why these are this curve is if your base is a fraction or a decimal smaller than 1. So not an improper fraction or not a decimal that has like a 1.5, but something that's smaller than 1. the higher exponent, the lower it's going to get. So it takes on that different curve, okay? So the domain of these arrows point left and right. The domain of these is all real numbers, or negative infinity to positive infinity. The range of my parent function is going to start at 0 but not include 0 because it can't include that asymptote, and point to positive infinity. Both of these arrows are pointing up. The second thing says the graphs of all exponential functions of the form f of x equals bx pass through point 0, 1, because no matter what power or what the base is, if I raise it to the power of 0, I get what? 1. So it doesn't matter if that's 295 raised to 0 power or it's 1/2, that answer is still 1. So from my parent, again, parent functions, not how it happens after shifts, but those points will always be there. Number 3 says if b is greater than 1, then it goes up, which is what we just talked about. It's increasing as you move from left to right. And if it's in between 0 and 1, then it's going to be falling as you move to left to right. Those are, that's number 3, and that's number 4. Number 5 says b to the x is 1 to 1 and has an inverse as its function. If I had, again, y equals 3 to the x, and I asked you if that was 1 to 1, remember that the test is that the x can't be an absolute value and it can't be raised to an even power. That's not going to happen here. So these are 1 to 1, and then the way that I would find my inverse, I switch my variables and I would solve. So I would take them, this is actually, we won't walk through that process because it's logs. We'll get there when we get there. You'd have to take the log of both sides of those to find the value, to solve for the value of y. But it does have a function, okay? And then 6 says the graph of f of x equals b to the x approaches but does not touch the x-axis, and that is a horizontal asymptote. So again, this is all based on the parent function. Once I start shifting these up, down, right, left, obviously these things are going to change. But all this information is true about the parent function. All right, so we're going to start like not knowing what this graph looks like, not using transformations, using a t-chart. So I'm going to plug in the same 3 points I usually plug in, which are -1, 0, and 1. And notice that we won't use the calculator this time. If this was on your quiz or test, you would not have a calculator. So what is e to the negative, or sorry, what is 3 to the -1? 1/3, right? If it's got a negative exponent, it takes that number and it shifts it to the opposite spot. If it's in the numerator, it goes denominator, denominator goes numerator. What is 3 to the 0? 1. What is 3 to the first? 3. So I'm going to plot those 3 points. -1, 1/3, 0, 1, 1, 1. Now if I had kept going, if I had plugged in 2, I would have gotten 9. I would have known it jumps a lot, okay? That's the exponential part. So I'm going to draw my curve as close to without touching the x-axis as I possibly can. And then it's going to increase exponentially, which makes that curve. Questions so far? So what's domain of this function? Negative infinity to positive infinity. What's range on this function? 0 with a parentheses to positive infinity. Okay, now go to B. So again, sorry? Because it can't actually hit the 0. There's no way to make an exponential 0. Nothing I raise that to will ever make it 0. Okay, so then x, again, -1, 0, 1. This time there's a negative in the exponent. So 3 to the -1 becomes 3 to the first, or 3. 3 to the -0 is still 1, because it'd be 3 to the 0. And 3 to the -1 is 1/3. So now I get -1, 3, 0, 1, and 1 and 1/3. Domain is still negative infinity to positive infinity. Range is still 0 to positive infinity with the parentheses on the 0. Questions so far? Yep. Mm-hmm. God bless you. All right, so the yellow is the first one. 1/4 raised to the -1 is 4. 1/4 raised to the 0 is 1. And 1/4 raised to the first is 1/4. And then the red is the second one. 4 to the -1 is 1/4. 4 to the 0 is 1. And 4 to the first is 4. Both have the same asymptotes. Both have the same domain, all real numbers. Both have the same range, 0 to positive infinity. Okay? But one is increasing and one is decreasing. The one with the whole number fraction, the whole number as its base is going to be increasing. The one with the fraction as its base is going to be decreasing. Questions on these? Okay, obviously we could start to add things after the exponent. We can add things in the exponent. So all of those things can happen. You can still just plug in your points and then plot it. So the same transformations that happen with all the other graphs that we talk about happen with these. If I add after the exponent or I subtract after the exponent, this is your shift up and your shift down. So adding shifts it up, subtracting shifts it down. If I add inside the exponent, this is like inside the parentheses. Adding shifts it left, subtracting shifts it right. If I put a negative on the front of the base, this flips it about the x-axis or makes it point upside down. If it's a negative in the exponent, it flips it left to right. So over the y-axis. If there's a number on the front of the base, which means my base gets bigger, obviously, then it's a vertical stretch. So the higher the number, the quicker it's going to go. If it's a fraction, then the smaller it's going to go. So the vertical stretch and shrink, just like if I had taken a string and pulled it up or squished it down. And then the last one is if there's a number being multiplied inside the exponent. And this is a horizontal shrink, which is like the walls caving in from the left and the right, which looks a lot like a vertical stretch. And then if it's less in between 0 and 1, then it's a horizontal stretch, which means it's being pulled out, which looks a lot like a vertical shrink. So those two look a lot alike, okay? When in doubt, you can plot some points. So we already found the graph of f of x equals 4 to the x. It was -1 and 1/4. 0, 1, 1, 4. This was my original f of x equals 4 to the x. So what happens if I add 3 here? Everything gets shifted up 3 places. So instead of plotting all new points, I can go 1, 2, 3, plot a point, 1, 2, 3, plot a point. And then I don't have graph, but I can do 1, 2, 3, plot a point. Now this horizontal asymptote was at 0, which means it's now at what? 3. Good. Domain of each is still negative infinity to positive infinity. The range of my parent function was 0 to positive infinity. The range of my new function is 3 to positive infinity. So the domain doesn't change because the arrows still point left to right. But when there is a vertical shift, my asymptote moves. If there was a horizontal shift, it wouldn't move. If it's a stretch or a shrink, it doesn't move. But if there is an actual physical shift up or down, then obviously my range is going to move. Questions so far? All right, so same thing. Start with the same one here, here, and here. Horizontal asymptote. But this time I've got x minus 2 in my exponent. What's that? A shift to the right, too. So all of these points get 1, 2 to the right, 1, 2 to the right, 1, 2 to the right. And there's my new curve. Did my domain or range change? Neither. Okay? So range only change. Oh, sorry. That's not. It didn't change, but it is 0 to positive infinity. Okay? Range only changes with a vertical shift or with a reflection, right? Obviously, if I flip it upside down, so a reflection on the front, then it's going to change as well, okay? So that's a negative on the base. If there's a negative on the base, it's going to flip it upside down. It flips it upside down, then my range switches the order. It goes negative infinity up to the asymptote. Questions so far? Okay, the one-to-one property is something hopefully you remember from algebra, but it means if the base is the same, then I can set the exponents equal to each other. So for any a being greater than 0, meaning it should be positive, okay, and not equal to 1, this is true if and only if the exponents are equal to each other. So if I had 2 to the x equals 2 to the 4th, and the bases are the same, I can ignore the bases and just set my exponents equal to each other. Remember, we already talked about it, but anything raised to the power of 0 is 1. That's not something you can actually compute. You have to just know it. So you solve using the one-to-one property. Let's look at A first. The left side says 3 to the x minus 2, and the right side says 9. Are they the same bases? No. Can I change them so they have the same base? What are you going to change, the 3 or the 9? Always change the bigger number. So how do I change 9 to be a base of 3? This is the same thing as saying 3 squared. Now is the base the same? So I ignore the base and I set the exponents equal to each other. And I get x equals 4. The best part of this is these are super easy to check. If I plug that back in here, I get 3 to the 4 minus 2, 3 to the second, which is 9. So these are easy to check. And there's times when we get to them, I'll note them, but there's times in which you must check your equations. Okay, B, I got 1/2 on the left-hand side, I got 16 on the right-hand side. What can I do to make them the same base? Because there's more than one answer to this. What is 16 as a power of 2? This would be 2 and 8, right? 2 and 4, 2 and 2. How many 2's are there? 4. So this is 2 to the 4th. Can I change 1/2 to be 2 to the something? What would it be? 2 to the negative 1 raised to the power of x means this is 2 to the negative x equals 2 to the 4th. Now the bases are the same, so I grab the exponents, negative x equals 4, and x equals negative 4. Again, I can plug them in and check. Negative means the 2's going to come to the top. 2 to the 4th power is 16. And the last one says 6 to the x equals 1. What's x? 0. There is no way that you can figure that out by working it out. You have to have that memorized. Questions on any of those? The natural base, E. So E is actually kind of like pi. It's a symbol that represents a number, okay? It's called the natural base, which, because when we get to logs, you'll see why, okay? But E as a number is 2.718281828, and so on and so forth. It doesn't end, it doesn't repeat, which means it's an irrational number. Your calculator has a little E button on it. If you just did E to the first, you would see that the number doesn't end, it doesn't repeat. And f of x equals e to the x is called the natural exponential function. So natural exponent because it's natural number, e, exponential because it's raised to an exponent, function because it has f of x. So this basically has all, so if I had f of x equals e to the x and I wanted you to graph it, it has all of the same characteristics of my exponential function. It's just like saying 2.7 to the x. So it's actually pretty close to the graph of 3 to the x, right? Because it's pretty close to that. You would have a calculator for a question like that because you'd have to compute the individual points, okay? So this is the explanation of why it's called the natural base. You don't even need to, like, I'm not going to ask you a question on this, but this is the explanation. The higher the n, so the higher I increase the exponent on a number, the closer it gets to e. It will continue to get closer and closer. Like the number here, I don't know if you can tell, but the change there is so minuscule and the jump is huge. The higher and higher it goes, the closer it gets to this 2.71828, like that whole thing, okay? So if you took 1 plus 1 over a base and you raised it over a number and you raised it to that same number, this pattern is always going to continually happen. All right, so example 7 says, use a calculator to evaluate the function of f of x equals e to the x at each value of x. Round your answer to 3 decimal places. So we'll do the first one together. I want to just do e to the 4.2. So on the calculator, you're going to find e, and e is above the ln button. You should have a little ln button, so you're going to have to hit second. You're going to have to hit ln, because that's where the e is. And then you're going to hit second, 4.2. And you're going to get 66.6. It said 3 decimal places, 686. And then the next one, you would do 125, and then you're going to do second, and then you're going to do ln, and it's going to bring up e, and then in the exponent, you're going to do 0.05 or 0.05. Oops, not times x, times 30. So these should be super easy, but if you get them wrong, there's like no partial credit here, because it means you just typed it into the calculator wrong. So you got to be really, really careful with this stuff, okay? It should be super easy. Your answer there would be 560.211. Don't round it wrong. Pay attention to directions, that kind of stuff. Your calculator does all the work for you. You just have to know how to use it. Questions on that one? All right, now that's graph involving E. So it says use a graphing utility to construct a table of values. Notice it doesn't say use the graphing utility to graph it. So we're just constructing the table of values, meaning I'm going to use the same table I've been using, but I'm going to use the calculator to actually find those values. So for e to the negative 1 plus 2, and you can actually type it in like that, or you can take it to the next step, which is 4e to the first, is 10.9. Then I'm going to do 4e to the 0 plus 2, which is 4e squared. And I get 29.6. And then I do 4e to the 1 plus 2, or 4e to the third, which is 80.3. So negative 1, 10.9, like let's say I jump these by 5s. 5, 10, 15, 20. I still won't get all the way up to 80, but you can get the idea. Negative 1, 10.9 is going to be here. 0, 29.6 might be around here. And then 180 is going to be way up there. And then I'm going to draw my curve. Now where should my asymptote be? Is there a vertical shift on this exponential graph? What's this doing? Is that a vertical or horizontal shift? Horizontal. What's this doing? It's a stretch, which makes it grow faster. Is there a horizontal asymptote there? Or is there a shift on the horizontal asymptote? So where's all my parent function horizontal asymptotes on my exponential curves? Huh? 0, which means this actually should come all the way down to here. We just don't have those points. So be really careful and pay attention. Like if you actually put that into your graphing calculator, 4e to the x it looks like that. So the y equals is 4e to the x plus 2. And then I hit graph, and notice that it comes all the way down to my x-axis. So be really careful, okay? Just because you don't have those exact points doesn't mean that it is not existing. So what's the domain on this function? Negative infinity to positive infinity. What's the range on this function? 0 to positive infinity with a parentheses on 0. So there's no vertical shift. If there's a vertical shift, that's when your range and your asymptote moves. If there's not, it's always at 0. With me so far? All right, last thing in this section is compound interest, okay? There's two types of interest problems. There's a compound at a certain number of times a year, and then there's a continuous compound, okay? So the equation for compounding at n number of times a year is this. P, which is your principal balance, however much money was put into it, times 1 plus r, the rate at which it's going, over n, number of times a year it's compounded, raised to the n, again, same thing, times t, which is time, how many years it's in that account. For continuous compounding, this means this is happening so fast that it can't be computed by the second. It's just continuous. And this equation is A equals P times e to the RT. So I call it PERT.
Wait, the only thing to RT is E? Or is it everything?
Correct. Yep. So you would take whatever is, this would be P, whatever that number is, and then e to the RT. So you're going to figure out what that is. You're going to raise e to that power, and then you're going to multiply it times p. Sure. So the difference between these two is compounded interest is happening a certain number of times a year. So sometimes something will say that you have money in an account, like a savings account or whatever it is, and it's compounding interest annually. If it's annually, how many times a year is that? Once a year. So my n is number of times a year would equal 1. If it says it's compounding monthly, this is 12 times. My n is 12. If it says quarterly is every quarter, right? How many quarters are in a year? 4. So that's 4 times a year. If it said semi-annually, twice a year. If it said weekly, 52. If it said daily, 365 times a year. You have to know those things, okay? Some people get a quiz and they're like, I don't know how many weeks are in a year. Tough luck, bud. Welcome to needing to know some common sense. If it was bi-monthly, what's that mean? Twice a month, which would be 24. But, okay. So sometimes it'll throw things in there. Okay. Okay, so notice one other thing, that this interest has to be in decimal form. So if I told you that it's the interest rate of 2.5%, how do I get from percent to decimal form? Move the decimal 2 places to the left. So this is 0.025, okay? It's the biggest mistake people make. You've got to move the decimal first. All right, so you can see it looks something like this. Find the accumulated value of an investment of $15,000 for 2 years at an interest rate of 3.2 if the money is A, compounded semi-annually, B, quarterly, C, monthly, and D, continuously. So let's start with the general information. What's the amount of money that's put in the account? $15,000, that's your P. What's the total amount of years that's sitting in that account? 2, so that's your T. And what's the rate? Good, 3.2%, which is going to be 0.032. Now what changes is the N. So for A, what's N? Semi-annually is? Twice a year. So P1 plus R over N to the NT is 15,000. 1 plus 0.032 over N, which is 2, to the N, which is 2, times T, which is 2. Now, if you have a graphing calculator, you can let that do all the work for you. You type in 15,000, open the parentheses, 1 plus, open the parentheses again, 0.032 divided by 2, close the parentheses again, hit the caret, and then 2 times 2, which is 4, or you could type it in as 2 times 2 as long as your exponent, as long as they both stay in the exponent. So 15,000, 1 plus, open the parentheses, 0.032 divided by 2, close the parentheses, caret, close the parentheses again, sorry. Two times 2, or 4, and I get $15,983, and this is money, so we round to what?
100.
Yep. 29 cents. It will not say that. Use common sense there, okay? If it's money, you're rounding to the cent, which would be the second decimal place. Questions so far? Okay, so now if I go to quarterly, what changes? Just the N. The N becomes 4. So this would be 15,000. 1 plus 0.032 over 4 to the 4 times 2. Now let me show you a trick on the newer graphing calculators that will save you some time. Okay, so if you have these, I think it's like the 84 and beyond. If you arrow up and you hit enter on this, it's going to duplicate it. So now all I have to change is my N's. So this is an N, and this is an N, and then I hit enter. So that's B. C is monthly, which means N is now what? 12, yes. So I can go up to do the same thing, change my N, but this time careful because the 12 is going to take over. So you could do 1, but then second insert 2. And then do the same thing here, 1 and then second insert 2. Hit enter and I get 15,990.02. And then D is PERT. So 15,000 E to the 0.032 times T, which is 2. 15,000 second E 0.032 times 2. And I get 15,991.39. Okay, so if you think about this, like the logic behind this, does it make sense that the more you compound interest, the more money you're earning? Yes? Do you understand what compounding interest even means? Like, at the end of, let's say I compound interest 10% a day, okay? So let's say I put $100 into account, and at the end of the day I earn 10%. So if I have $100 at the end of today, how much money do I have? 10% I'm earning. What's 10% of 100? 10. So how much do I have in the account at the end of the day? 110. So now tomorrow when I start accounting or accruing money, it's on that new 110. You with me? So now what's 10% of 110? 11. So tomorrow I earn $11. So now I'm at what? 121. So every day it goes up, and the more you compound it, the more money you make. So when you compare these answers, the PERT should always be the highest, first of all, because it's compounding so continuously, it's not even a number. The second thing is if it's compounding monthly, it's over annually or semi-annually, the monthly should be higher. Okay, the more times it's compounding, the higher the money. If it's 365, like if it's daily, it's actually pretty close to PERT. But the longer it sits in the account, the bigger the difference will be. So if it's 2 years to like 100 years, you're going to see a bigger jump, obviously. Questions on anything we talked about today? So the introduction into exponential. Everybody's good? Tomorrow we get to talk about logs. So exciting. Everybody's favorite. All right, I'm going to open the assignment on WebAssign. Okay. Make sure you are graphing by hand and then selecting your graph.